Hello everyone, and welcome to today's Chem lesson. Today we're going to talk a little bit about two different topics. First is Table H, this thing we see on the screen here, which is going to tell us about how the boiling point of a liquid changes when the air pressure changes. And the second thing we're going to talk about is the idea of heat flow and how heat transfers from one object to the other. First, let's take a look at Table H together. Table H shows us four different liquids, and it tracks with this bold line how their boiling points change as the air pressure changes. Now, why does this happen? If we think about a pot of water and how that water needs to boil, these liquid particles, these liquid molecules, need to make their way in to the air, into the gas phase, and mix in with the gas outside. Air pressure, right, the regular pressure of the air pushing downwards, makes that difficult for the water molecules to do. Sometimes when they get into the gas phase, they get immediately pushed back into the water and they're into the liquid phase again. The less air pressure that there is, the easier it is for those particles to join the gas phase, to become gases and mix with the air. So at sea level, water has a boiling point of 100 degrees Celsius. As we travel higher and higher into the mountains, as we get to less and less air pressure, the boiling point of water is going to decrease. It's going to be easier to boil the water. Now, this means that if you're up in the mountains and you're trying to cook pasta, you're going to have to cook your pasta for longer. Because instead of cooking the pasta for 10 minutes at 100 degrees Celsius, if you just followed the regular instructions, you'd be cooking it for 10 minutes at 80 degrees Celsius, and it wouldn't get as much heat. It wouldn't cook as much. And so you'll see sometimes on food packaging, right, on pasta packets or on, cake mix or brownie batter, you'll see what the high altitude cooking instructions is and how long you should cook these things at high altitudes, because the temperatures that you're cooking at are going to change. Right? Water will behave differently at those higher altitudes. Now, in terms of questions being asked of you, Table H is actually really simple. You're looking at air pressure, you're looking at boiling point, and you're looking at identity. Any question that refers to Table H must give you two of these three things, and your only job will be to find the one they don't give you. If they give you identity and air pressure, you're going to find whatever intersect they're talking about and follow it down, not in a line that crooked, but you're going to follow it down in a straight line and find the boiling point. If they give you boiling point and air pressure, you're going to find the intersect and look at the identity. If they give you the identity and the boiling point, you're going to find the intersect and read it across to find the air pressure. Now, an important thing to note here is that the scale for our vertical axis is different than the scale for our horizontal axis. each one of these boxes going up is an increment of 10. All right, 150, 160, 170, 180, 190, 200. But if we look at what those boxes are worth going left to right, 0, 5, 10, 15, 20, 25. They're worth 5 each here, but 10 each here. Right, just something to keep in mind and pay attention to as you look at these diagrams. Let's try a practice problem. Right. If the pressure on the surface of propanone is about 90 kPa, what will the boiling point be? Here, if we look, we're looking at propanone. They gave us the identity, and they gave us the air pressure. Right, so we're looking at 90 kPa for propanone, and we're trying to follow that down the line to see what our boiling point will be. It's somewhere between 50 and 55. The only answer that is remotely close to that is choice 2. What about a similar question? What about this question? Water will boil at a temperature of 70 degrees Celsius when the pressure on its surface is blank. Here, our correct answer is choice 3. 70 degrees Celsius, following it up to get to water, following that along to reach the pressure, 10, 20, 30. So we pick our closest answer. Right, notice they give you 2 of the 3 things and ask you for the third. Right here they give you the identity and the boiling point, ask you for the pressure. Before they give you the identity and the pressure and asked you for the boiling point. There's only so many variations of this problem. Now, the other thing I wanted to spend some time talking about today was the idea of heat flow. This is something you've experienced multiple times. Right? Heat flows from the hotter thing to the colder thing. Heat flows from hot to not. If you put 2 things in contact with each other, like these 2 green boxes, the hotter thing will heat up the colder thing. And so we'll see heat transferred from our 70 degrees Celsius substance to our 30 degrees Celsius substance. Right? 70 degrees is going to go down to 60, heat this up to 40. 60 is going to heat this up to 50 and 50. Right? Once you hit a balance, once these 2 things reach an equilibrium, there is not going to be any more heat transferred. Any heat that is transferred will immediately be transferred back. But we've seen this happen over and over again in day-to-day life. If you've ever used an ice pack before, an ice pack works by pulling the heat out of you. It is so cold that it suctions the heat out of you and absorbs that heat for itself. If you've ever used a heat pack, right, one of those little glove warmers in the winter, a heat pack does the exact opposite. It is so hot that it warms you up. If you hold a piece of ice in your hand, heat gets transferred from your hand into that piece of ice. And these heat transfers occur until we reach an equilibrium. And once we reach that equilibrium, our heat transfer is not nearly as drastic. It's just a little back and forth. It'll go from 50 and 50 to 49 and 51. And then it'll switch 51, 49, and then it'll switch 49, 51, back and forth and back and forth and back and forth. So sometimes when we ask questions, that's not what I would like to do. Apologies. So sometimes when we ask questions, we'll see things like this. And they'll say, what temperature will these things end up with if we leave them alone? Right? What temperature are these things going to reach equilibrium at? Sometimes it's as simple as just seeing what these two things are going to average out to. The 80 will heat up the 10 until both things reach the balanced temperature of 45 degrees. Right, this will get colder and colder. This will get hotter and hotter. And they'll eventually reach a balanced equilibrium at 45 degrees. Other times, they ask you the same concept, but a little bit more wordy. Sometimes they give you the same exact question, but they make it look much more complicated than it is. If we read this question carefully, we're putting two things into contact with each other. We want heat to flow from X to Y. So which situation, which setup is going to let us see heat going from X, the hot thing, to y, the cold thing. Choice 1 has x and y at the same temperature. There's not going to be heat flow here. Choice 2 has x at 10 degrees and y at 5 degrees. X is hotter than y, so we're going to have a heat flow from x to y. 3 has y hotter than 10. 4 also has y hotter than x. And choice 3 and 4 have y hotter than x, so we're going to flow from y to x. The only choice that shows heat flowing spontaneously from x to y is choice 2. It's the same concept. They're asking you the same thing. Can you tell which one is hotter? Heat will flow from the hotter thing to the colder thing. Which situation lets that be true? If you read the questions carefully, you won't get tripped up. With that, I'm going to transition us over to our Zoom for questions, comments, concerns, and attendance. And I will see you there.